Okay, welcome everybody to today's lecture, which will be on short-term memory. Okay, so let's again, as usual, start with a brief introduction into short-term memory. And I would like to start very broad. So generally one can, it's pretty loud today, isn't it? So generally, one can say that memory consists of multiple stores, and I'm sure most of you are familiar with that idea. So when we start very early in the processing, we will speak about this in more detail in a moment, that it all starts with some very low-level sensory stores, which hold information extremely briefly, so only for 50 or 100 milliseconds or something in that order. And they're specific to each sensory modality. So for vision and audition, we have separate stores here. Then we have the short-term memory. So information is passed on from the sensory stores to short-term memory. And short-term memory holds information in the order of something seconds to minutes. And it is assumed that it has a limited capacity. As you all may know probably, that you can't just read a whole page of a book and then immediately remember and recall that. And lastly, we have a store which is called long-term memory, and here it's assumed that information is stored over very long periods of time, maybe even a lifetime or something, and that it basically has an unlimited capacity. Okay, and today we will focus on short-term memory and also on sensory stores, and next week we will speak about long-term memory. However, these concepts are not always totally independent from each other. So we will see that we will touch on long-term memory a little bit, and if you have read the chapter in the book, then you will see that I won't cover some of the topics which are in the chapter, because I thought they fit more neatly into next week's topic on long-term memory. For instance, how information is better stored into long-term memory and things like that. Okay, so short-term memory is the most common term. However, it's a little bit a vague term. So there are some synonymous words to that. So some people call it primary memory. That term was introduced originally by William James in 1890. Maybe called active memory or immediate memory. But short-term memory is probably the most common term for that. Let's start again also with a brief definition of working memory. And short-term memory can be defined as the capacity for holding a small amount of information in our mind in an active, readily available state for a short period of time. So we have a brief period of time, we have a little small amount of information, but this information is in an active state, so that it's accessible to our consciousness and we can use it for manipulations, for instance for mental arithmetics or making decisions or things like that. There's a little bit of an even greater confusion with terminology, let's say, between the terms short-term memory and working memory. And a lot of people use that synonymously. And there is no really right or wrong to say it's the same thing or not. It's really about your concept. But quite a few people would say, okay, nowadays we can differentiate these two concepts, especially when we speak about, or the people who are in the domain of working memory. And the difference is basically that short-term memory is really about the storage of information. So just keeping information in our memory, maintaining the information. So for instance, I could ask you to remember a phone number, 555-3421. And you have to keep it in your mind until you find a pen to write it down, or you can dial the number or something. So that would be short-term memory. Working memory, according to this view that these two things are something different, would be again the storage of this information, the short-term storage. However, in addition, it would be the capacity or the processes to manipulate this information. So to stay with that example, we could say, okay, please remember the phone number 555-3421. And then I say, oh, I'm sorry, I made a mistake. Please swap the last two numbers. It's not 34, but 21, but 12. So in your mind, you do the operation of swapping the two letters. That's a manipulation of the contents of your memory. And people would say, okay, that is working memory and not short-term memory. And for instance, in investigations in the area of cognitive neuroscience with functional brain imaging, it has been shown that the mere maintenance of information and the storage or the manipulation of information actually is located in two slightly different brain areas. So it really seems to be that it can be dissociated. So, however, also in the Gobet textbook, you will see that short-term memory and working memory is really used pretty much synonymously. Okay, when we speak about memory, we have to do a little bit of a conceptual distinction. And one is about the architecture of memory. And that regards the questions how our memory system is organized. For instance, how many different memory stores do we have? Do we really have a separate short-term memory and a separate long-term memory? We will see later on that there are models who say, no, we don't have that. Or do we really have that at different stores? So it's the architecture, the structure of that. And then we have the processes which work within this architecture or structure. And that is, for instance, how do we retrieve information? How do we put information into long-term memory so that we have, for instance, an index system or something? Or what is the process of transfer from one into the other? Okay, so when we speak about memory, then of course we want to kind of investigate it. We want to know how good is our memory, or how good is it in the people in different conditions. So the question arises, how can memory actually be tested? And that's pretty straightforward, and many of you have done that, I think, in last term in the research projects. Quite a few of you worked with memory paradigms. So one approach is we let participants just memorize items, can be words, pictures, whatever, and after some time we test how many they remembered. Now, that is the very basic paradigm and idea how to test for memory. However, there are different ways how we can actually do this test. So how do we test for the memory? And one option would be free recall. So, for instance, we give them a word list on a sheet of paper, and after a minute we take the paper away, give them a blank sheet of paper and tell them write down all the words which you still remember. So that's free recall. Another way to approach that is a recognition test. So in this case, so free recall would just be a blank sheet, and a recognition test is usually done, you present two items to the participants, for instance, two words, and only one of the words is new, and one of the words is new, they have never seen before, and one of the words is old, they have seen before, and they have to decide which one did you see before. Or you have them learn 10 words, and then you test their memory for 20 words. And for every word they have to say, okay, I've seen that before, I recognize it, or I don't see that before. Usually you get better kind of memory performance when you test recognition, because it's easier to recognize something than free recall. So when we look at these type of tasks, this short-term memory task, then we can, when we look in a bit more closer detail, we can identify 3 stages or phases which are common in every of these tasks. So the first is we have to present the items which are to be remembered. And here the information is encoded into short-term memory. It can be words, can be pictures, whatever. And we have quite a few parameters which we can vary to change the paradigm to suit our needs. Maybe we want to investigate different things. For instance, we can present all items at once on a sheet of paper. However, we could use a PowerPoint presentation and present one item after the other. We can vary, when we do one after the other, the duration of the presentation. We can show items for a second, a new item every second, or a new item every 3 seconds. Gives you more time to encode the information. We can have like a blank interval between 2 items, which gives you time to rehearse that or not. So these are the most typical things we can vary during item presentation during the encoding stage. Then we have the retention interval. That means we have presented our items, let's say a sheet of paper, we take that paper away from them. Now, this is basically the time where we have to keep our information active in short-term memory, the storage period. And the crucial parameters here, we can vary the duration. So if you take it away and immediately give them the option to recall everything, your performance will be higher as compared to let them wait for a minute before they can recall. A very crucial question, as we will see in a moment, is whether we allow rehearsal. Rehearsal means you tell them some words and you can go through that in your mind. Can't share that, can't share, and so forth. We can prevent that by adding an additional task. For instance, when we say during the retention interval, please count backwards in steps of 3s from, let's say, 300. So 297, 297, 294, 291, and so forth. So it's a quite demanding task, which gives you no way that you can still rehearse your memory items. And then finally we go to the test phase, where participants have to retrieve the information they have stored. And here we have again a couple of parameters. So one question is, do we do a recall task or a recognition task? And that depends basically on our research question which we have. We can ask the participants to recall the items in the exact serial order as they have been presented, or we say, oh, in any order they wish. We can impose a time limit, everything they remember within a minute or something. And especially if we use computers, we can measure, so accuracy, of course, we can always measure how many percentage correct did they remember. And with computers, we can, in particular in a recognition task, we can measure the time it takes them to say, yes, I've seen that before, or no, I didn't. Okay, let's, as a demonstration, let's do such a free recall task for yourself. So it would be good if you get a sheet of paper and a pen, so that you can do the recall phase of that. Okay, then in a moment you will see on the PowerPoint 12 words, and each is presented for 2 seconds. Try to memorize them. Please don't write them down when they're shown here, because that makes, of course, the whole test pointless. And afterwards, when it's presented, then please try to write down as many words as you can remember. Okay. And you can use any order if you want. So it's a free recall task. Okay, ready to go? Okay, I think everybody's finished with writing. Okay, these are the words which had been presented. So let's see, how many did you remember of them? There were 12 words. Okay, let's make it a little bit more specific. Please raise your hand. Who remembered fashion and or endorse? Okay, virtually everybody. Who remembered create and or paper? Again, virtually everybody. Who remembered sponge and or dolphin? Oh, you have a good memory. Who remembered all 12 of them? Oh, okay. So what you will find if you do that task, that most people have a better memory for the first words, which were earlier in the list. And in addition, that memory is better for the last words, which were here. So this has been a finding which has been shown many, many times and is called the serial position effect. It was first described by Hermann Ebbinghaus quite a few years ago. And this curve shows you here on this axis how good your recall is, so the higher the better in percent. And here, the position of the word or the item, the picture, in the sequence. And this is called the primacy effect, that you remember the first words better, and that you remember the last words better is called the recency effect. And that's a very, very strong finding. So how can that be, this finding be explained? So the primacy effect, the idea here is that the words can be rehearsed more often. So for instance, if you see the first word for 2 seconds, you can go fashion, 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 fashion in your mind. Then the second word comes up, fashion, endorse, fashion, endorse, fashion, endorse, and so forth. And due to that longer rehearsal, there's a higher likelihood that it's actually already encoded into long-term memory. So the first items have a higher chance or proportion of being in long-term memory, so that you remember them better. Then we have the recency effect, that we remember the last words better, and that is probably that the last words are just still in our short-term memory. We just heard them, they're still there. We said it's a storage which lasts a couple of seconds until a minute or so. And support for that is when we, in this case, our retention interval was basically 0. Directly after the presentation, you recalled. However, if you have a brief retention interval, let's say 30 seconds, and you fill that with a task so that you can't rehearse, the recency effect is strongly diminished by that. So that supports the idea that it's just the short-term memory of the last words, which is due to the recency effect. Okay, so to conclude or summarize the introduction, we have seen that short-term memory is a limited short-term store, and that typical short-term memory tasks have 3 stages: the item presentation, the retention interval, and the recall, and each has many parameters. And memory systems can have at least 3 functions. We have the encoding of information, we have the storage of information, and we have the retrieval of the information. And now we have seen, we have in a free recall task with immediate recall, we get a U-shape serial position curve, which is a very central finding. The primacy effect is probably due to long-term memory storage, and the recency effect due to short-term memory storage. Okay, any questions on this first bit? Okay. Let's go on to something which is called the chunking hypothesis, and this is related to memory performance again. How much information can we store in our memory? And again, a demonstration. Please try to remember as many letters as possible of what you will see in a moment. Okay, it's likely that you didn't remember many letters. Okay, another demonstration. Again, please try to remember as many letters as possible. Okay, did you remember more or less letters? More letters, yeah. It were actually the same letters in the first and second demonstration. So, okay. This time you were able to chunk them into words. So it's not independent letters anymore, but you were able to group them, chunk them into words. Okay, one last demonstration. We can go more quickly through that. Probably even easier to do that task. So you don't need to write that down now. So, okay. This time you were able to chunk the letters not only into words, but even the words into a larger chunk of a well-known sentence you probably know. And chunking was first proposed by Miller in 1956, and it's that Miller, when you remember the first session, who contributed, so to say, to the cognitive revolution with this paper about short-term memory. It was one of the early papers who said, let's say, behaviorism aside and said, okay, let's look at the cognitive performance, at memory, at a process which is hidden to direct behavior, where we don't just have stimulus and response. And therefore had his share in starting the rise of cognitive psychology. And this paper is called The Magical Number 7 plus or minus 2, some limits on our capacity for processing information. And it's probably one of the most cited papers in psychology ever. It's cited over 18,000 times. And that doesn't mean like in newspaper articles, that means in other scientific articles. So quite a few times. And his key observation in this paper was that this capacity of short-term memory did not directly depend on the amount of information as such. So for instance, counted by the number of letters, which from a computer point of view would be the amount of information, but how this information can be grouped into chunks. So the definition of a chunk, a more formal definition, is that it's a collection of elements which have strong associations among each other. However, they have weak associations with the elements within other chunks. So in words, for instance, the particular sequence of letters have very strong associations with each other, but not strong associations with the letters of the next word. Chunks are based on previous knowledge. They don't come naturally to us. And for instance, it has been shown that we first have to learn letters before we can chunk them into words. So when children learn in school, they first have to learn the letters before they learn the words. It has been shown that other way around, learning is much less efficient. So that also means that chunking is highly subjective. What is a good chunk to you may be meaningless to another person. So words in another language do not form chunks. If you have that, then probably, unless you speak German, you don't see much sense in that. However, if we use the same words in English, then they suddenly make sense and they chunk together. So that we have that. And the key message of Miller was that our short-term capacity is 7 plus minus 2 chunks of information. Not letters particularly, but chunks of information. There were quite a lot of follow-up studies trying to investigate chunking in more detail, and we want to go through one study who nicely shows that. And participants had to do this task, and they had to go through 3 conditions. In the first condition, they had a consonant, vowel, consonant, pseudo words presented, a couple of them per trial, and later on memory was tested. So this was like a pseudo word, and it consists of 3 letters when we think about the amount of information kept here. And because it doesn't make sense to us, you could say, well, it's 3 kind of chunks, and each chunk is just 1 letter. In the second condition, he had 1 proper 3-letter word, like dog. Again, we have 3 letters, like in these examples. However, we only have 1 chunk. And finally, he had 3 proper 3-letter words, like dog, bar, pet. So when we define information as number of letters, we would have 9 letters. If we define it as number of chunks, we have 3 chunks. Now the crucial question is, how is information defined in short-term memory? If it's on the basis of letters, these 2 conditions should be similar because they both consist of 3 letters. If it's on the basis of chunks, this condition and this condition should be similar because they both have 3 chunks. And it turned out that indeed condition 1 and 3 result in pretty similar performance. So it's actually the chunks of information which count for our short-term memory capacity. Okay, to summarize the chunking idea, it's the grouping of units of information, like letters, into groups, like words, which can later then used as units themselves, for instance in a sentence. So by this hierarchical thing, we can store much more information. Chunks are long-term memory structures, and it has been shown that in some of these experimental tasks, it takes just around 5 to 10 seconds, or can be around that time, to learn a new chunk, and use it later on as individual unit. And that short-term memory capacity is limited by the number of chunks. So if you are like a memory artist, then one of your tricks might actually be that you have just memorized a huge number of chunks which are hierarchically organized, so that you immediately recognize huge patterns which are just one bit of information to you. Like in chess players, they look at a board and say, oh yeah, that's that setting that this player used in 1954 or something like that. And they immediately see that, and it's one chunk for them. It's a spatial arrangement of like 12 or 15 figures on a chessboard. Okay, any questions on that bit? Okay. Now, after these basic introductions, let's speak about some models of short-term memory. And we want to go through 3 models. The first one is one among the earliest models, and it's called a multi-store model. We will see in a moment why it's called like that. It has been proposed by Atkinson and Shiffrin, and it's so popular, has been so popular that it's also called the Atkinson-Shiffrin model or modal model. And it's the idea that memory consists of multiple components. And what they actually proposed was a whole cognitive architecture where memory was the most central component. So you will see that there are a few more additional things in there. And it has been very influential in the ways people thought and conceived memory, and it initiated a lot of research in testing the model, testing the predictions of the model. Okay, so we have 3 major stages in that model. And as I said, it's a whole cognitive architecture, so it really starts from that we receive input from the outside world. Then this input generates some cognitive processing, for instance rehearsal, if we stay in the domain of memory. And then we produce some behavior based on this cognitive processing. And that's the output of the system. And in their model, the memory stores are the places where information is maintained and processed. In addition to the memory stores, we will see we have control processes, which are kind of hierarchical above that and control the flow of information, where we put attention and things like that. Okay, let's go through the model step by step. It all starts with stimulus input from the outside world. And for ease of things, it can be a word list or a word, or it can be something else we see. And that information first enters the sensory registers. And they hold information very briefly until it is forwarded to the short-term store. And we have one store for visual information, that's called the iconic memory, and one store for auditory information, that's called the echoic memory. So we have these two different type, modality-specific type of stores. Then information is passed on into the short-term store from the sensory registers, and this short-term store is modality independent. It holds and processes information of visual, auditory, tactile input and nature. They defined the short-term memory span around 7 items and probably based that on the results of Miller as well. And they proposed that rehearsal is required to avoid forgetting. If we don't rehearse, information, memory content will fade away and we forget it. Then we have the long-term store, and this contains all information which we have acquired through learning. So information is stored permanently in this model, and an infinite capacity is assumed, so that we can store everything for an infinite amount of time in long-term memory. Okay, this is the whole model. So we have gone through these memory bits. Then we see that we have control processes here as well. And these processes control, for instance, what information enters the short-term store. For instance, by attentional filters, as we have spoken about last week. Also, they control how information is passed back and forth between long-term memory and short-term memory. And finally, these control processes determine what processing is going on in the short-term store. So, for instance, whether we should rehearse information or not. As I said, this model was very, very influential, but it was one of the first models. And naturally then, it turned out that quite a few very central assumptions of the model were actually incorrect. So one is that short-term memory is independent of modality. That short-term memory is a unitary storage for auditory and spatial visual information. It turned out we have separate stores in short-term memory for auditory or verbal information and for visual spatial information. So we have different subsystems here. Another incorrect assumption is that, again, a simplification of the model, that short-term store is a single unit with respect to maintenance and processing. And Atkinson and Shiffrin assumed that the maintenance of information and the processing of the information, they demand a common resource which is limited. So if I have to maintain something, I have less resources to do something, to do processing. And if I do heavy processing, then I have no resources left to maintain something. However, here again, it turned out that you can create tasks which require maintenance and processing, and they don't interfere actually that much. So it seems to be it's two different processes. We will speak about this evidence in more detail when we get to the working memory model of Alan Baddeley. So In summary, it was a very good model, but actually it's a bit more complex, the real world, than their model has proposed. Okay, do you have any questions on that model, regarding that model? Okay, so let's have a look at a different way how memory can be conceptualized, how you could propose a model for memory. And we have a look at a model which is called a unitary store model. And this is by far not as popular as the Atkinson and Shiffrin model we just spoke about, or the baddeley model we will speak about in a moment. However, it's a good way to illustrate in how different ways you actually can think or build models of things. Because we all think, oh yeah, we have short-term memory, long-term memory. This model actually has a different conceptualization. And the idea is we only have one memory store. That's why it's called unitary store models. And that is long-term memory and nothing else. However, the contents of long-term memory, let's say the individual items or storage representations, can be activated for a brief amount of time. And these activated bits in our long-term memory actually constitute short-term memory. That's the idea behind that. A person proposing such a unitary model was Nelson Cowan, and his theory looks like that. Let's go through that. So this big white box is the long-term storage, long-term memory. And all these dots represent bits of information we have stored. Maybe words, maybe pictures, whatever. So these are our items in memory. Now, some items in this memory, like this blue box, can be activated. For instance, by attention, by task demands we actually have. And these constitute short-term memory. And then he added a third layer here, and that is the items we actually put our focus of attention on. And this is where processing happens. So in this example where we said, okay, with the phone number, please switch the last 2 digits, then we would have to focus our attention on this one single information in our short-term memory and work with that. So from a conceptual point of view, it's very different to the other models. And there is some evidence in support of that. Okay, that's all basically what I just said. So it's a rather new model, and there's not too much evidence on that. And probably assuming that short-term memory really is only and purely the active part of long-term memory may be an oversimplification again. However, my main point is that don't always think in boxes, like, of course memory, we know we have short-term and long-term memory, so it must be 2 different things. You can realize or implement it in a different way. And it turns to be out what's the best way for cognitive psychology to describe it, and of course what's the neural underpinnings, how does our brain do it? Do we have a separate neural store for short-term and long-term or not? And it actually looks like that we have a separate store. Okay, any questions on the unitary store models? Okay. Then we have a quick break, a little bit earlier today, and then we go on with the baddeley model. Okay. Sorry. Let's go on then, and let's speak about the working memory model of Baddeley and Hitch. So they proposed in 1974 for the first time their model, and it actually was based on the model of Atkinson and Shiffrin. But they had some findings which were not in line with their model, like that we have subdivisions of short-term memory store, which led them to propose their other model. And it turned out to be a very popular model. So the Baddeley model of working memory is one of the central cognitive models in psychology, I would say. So that's really an important one. Okay, and they proposed that short-term memory consists of a couple of components. The first one is the phonological loop, or sometimes abbreviated as PL, and that's kind of responsible for language or speech-based coding of information. So it's like our inner voice. When you rehearse something, a phone number, then you do 1, 2, 3, 1, 2, 3, 1. So you speak that in your mind. That's the phonological loop you're working with. Then we have the equivalent for visual spatial information. It's called the visual spatial sketchpad, or sometimes scratchpad as well, or VSSP, and that's kind of the inner eye. So we try to remember a code like spatial information, a layout. When you, for instance, try to find your way out of a maze, then you may use that. If you have to do tasks which are purely spatial, which you can't easily encode verbally, then you use that. Then later on, only in the year 2000, Baddeley proposed a third component. So the original model had as components of short-term memory only the phonological loop and the visual spatial sketchpad. However, later on he proposed the episodic buffer, and the information of, or the idea of the episodic buffer is that it kind of links and integrates all the information in these, they are often called slave systems, and also from long-term memory, to bind the information together into one coherent representation, or one unified percept. Now, by squeezing it all down here, you may guess there's some more coming up, and that's what he or they proposed to be a central executive system of working memory. And that is kind of a supervisory system which controls these subsystems. So this CES, the Central Executive System, is supposed to be modality free, so independent of whether it's verbal or spatial information. One of the main responsibilities is to control attention. So where do we focus our attention, switching attention, things like that. And it's involved in complex processing tasks. So when I ask you like this, swapping the last two letters of the phone number itself is represented here, but when I want to do the swap, I need the central executive system to do this operation. So this is the processing component, while this is the pure maintenance and storage component of memory. Okay, so what evidence is there in favor of this model? And Baddeley made very wide use of a dual task paradigm. That means that their participants had to do two things at the same time, which is quite challenging actually, but it was interesting, the results. And let's suppose the primary task they have to do is a short-term memory number recall task. So you get a list of numbers, have to memorize them, have a retention interval, and then you have to recall them. And now he added a variety of secondary tasks, which are, in this example, quite complex, resource-demanding tasks. Could be reasoning. You see sentences on the screen, and you have to say whether the statement in the sentence is true or not. Or another task, which is sounds simple but actually is quite demanding is called random number generation. When I ask you to just give me a sequence of random numbers between 1 and 9, like 1, 7, 3, 9, 4, it's demanding because we tend to fall into sequences of doing 1, 2, 3, 4, 5, which we have to inhibit. So we have to always memorize what did I just say, the last 2 or 3 items. These type of tasks he used. And when you remember, Atkinson and Shiffrin said, well, short-term memory is both in a unitary system. So these two tasks should really interfere with each other. Performance should break down in both tasks profoundly as compared to when I do them individually. However, Baddeley and Hitch found that they really can be done largely in parallel. You have some costs, but not nearly as much as expected based on the Atkinson and Shiffrin assumption. So that's another example where you have an empirical study which is done to decide between two models, which model is true. And these are the studies which are nice and beautiful and bring science a step forward, where you say, okay, if I get that outcome, this model is true. If I get the other outcome, the other model is true. And then you run the study, and it's in favor of that model. Of course, reality is not always that straightforward and easy and clear-cut, but sometimes it actually is. So Baddeley and Hitch concluded that the storage in the phonological loop and the visual spatial sketchpad is separate from the processing, which is done by the central executive, because this was a storage task and this was a processing task. They used the same logic to show that we have at least 2 different short-term memory systems, one for auditory, one for visual information. So the primary task, again, was a verbal short-term memory task, like number recall. And the second task was a visual spatial short-term memory task, and they used, for instance, the so-called Corsi block task. How does it look like? In the Corsi task, you have, as a participant, you sit there, and it can be boxes on a sheet of paper, for instance. And participant rests their finger here, and now you, as the experimenter, tap the different squares in a certain order, like this, 1, 2. Of course, for the participants, they only see the empty squares. This gray shading is only for illustration. And as participant, you have to repeat the sequence, the spatial sequence. It has been shown that this type of task is done in a visual spatial representation. You don't memorize that verbally. And again, they found that when you combine the two tasks, the verbal and the spatial task, that there's much less interference between the two tasks as you would expect. Or for instance, if you actually combine 2 verbal tasks, a number recall combined with a word recall, that doesn't work very well. So they actually have quite strong evidence that we have at least these 2 storage systems, phonological loop, visual spatial sketchpad, which are in addition independent of the processing bit. Okay, so let's look at the phonological loop in a little bit more detail. And as we said, it's short-term memory for speech-based information, and in later research it was broken down further into 2 components. One is the phonological store, and this holds information like words online or active only passively in an acoustic format, so how in the way we speak it. And it has been shown that the information in this phonological store decays roughly within 2 seconds if it's not refreshed. How can we refresh it? That can be done by rehearsal. That's why we rehearse, so that information does not fade away. So they propose that as a second independent component. So memory items in this phonological store are refreshed item by item. And that's exactly what happens when you have to remember. We do, oh, it was chair, table, dish, chair, table, dish. You go through that item by item. And it's pretty much comparable. You may know these artists in a circus or sometimes when they have these long poles and they balance a plate on there by spinning the poles and the plates very quickly. And when you go through there, they have to start again here and then do one after the other, start at the beginning again. And if they become too slow, if it takes too long to go all through them, what happens? It falls down. The analogy in memory would be it falls out of our memory. So what actually Baddeley proposed is that our verbal memory is limited by time, not by information, amount of information. It should be reflected in time. We will see that in a moment in a bit more detail. Okay, the visual spatial sketchpad has a roughly analogous representation, and here it's assumed that the capacity is around 3 to 4 items, or not assumed, it has been shown experimentally. And again, we need rehearsal to prevent decay here. And it has been later, you see only in 1995, suggested that also the visual spatial sketchpad can be subdivided into 2 components. One is the visual cache, which just holds visual spatial information online. And the other one is, which is called the inner scribe, which carries out some operations on this content. For instance, if you mentally want to rotate an object in your mind, then it's assumed that this is done by inner scribes, while the visual cache is just the maintenance of that. So visual spatial sketchpad has separate mechanisms to process the information. Okay, and it has been shown it's separate for the visual format, so for instance form, shape of objects, and the spatial format, like this Corsi block task, where we really have to remember a spatial layout or a path or something. And to investigate that, what you want to make sure is that people can't encode the visual thing verbally. So if you just present them squares and triangles, they will just say, okay, I've seen a square, and remember square, triangle, square, triangle. What you need are forms which people can't easily transform into words. And I know from some researchers, for instance, that they used or employed Star Trek. And some of you may know that you have this race of Klingons in Star Trek which have their own alphabet. And they used certain letters. This is not a very good example because it closely reflects our alphabet as well. But you have some letters there where people really find it difficult to verbalize them, especially if you take a couple of similar looking ones. And by this you can make sure that people really use the visual spatial sketchpad for memorizing the items. Okay, any questions on the working memory model of Baddeley and Hitch? Okay. So, when I created this lecture, I thought for quite a while how to structure it, because information is so overlapping on the one hand and non-overlapping on the other hand. And it may look kind of that we go through the same things now once more. However, this time we go through that in a very generic way, which is independent of the models we spoke about. So really studies and evidence on how sensory register works, the verbal short-term memory and the visual spatial short-term memory. And the studies we will see and discuss are often done in the context of one model, but they are valid for all models. So it might be a little bit confusing if I say, okay, this has been done in the context of the phonological loop, but it's generally valid for verbal short-term memory. So that's the reason why we go through the different stores once more. However, now we of course discuss different things with that. So the sensory registers appeared in Atkinson's model, in Cowan's model. However, Baddeley didn't make any explicit statements on that, but he surely wouldn't say that there are no sensory registers. He was only just interested in what happens after those registers or buffer stores. And there's a very interesting, intriguing study by George Sperling, who basically found or discovered these sensory registers. And he did a memory task with his participants. And participants were asked to fixate a cross on the screen, as usual. And he presented a random array of letters on the screen. However, he presented that only for 50 milliseconds. So extremely brief, it's just a flicker you see. And then he asked the participants to recall the letters. And what he found is that the maximum participants were able to recall were around 4 letters. So the memory span in that task. So not very high. Okay, let's have a quick demonstration with the Sperling task. So in a moment you will see 3 letters flashed very briefly, and you can try to remember them. If it was visible here, probably it's not too difficult to do that. It was R, N, and F. However, now you will see 12 letters. 3 rows of 4 letters each. Try to see, you don't need to write that down, but just try to see for yourself how much you can remember then. Not very much, is it? Okay, suppose you have a bit of a better condition. Now Sperling found that indeed participants again were around 4 letters, 3 to 4 letters. But then, no idea how he came to this idea. He introduced a variation to that paradigm. And that is that he asked participants only to report 1 of the rows. And that was indicated by the pitch of a beep presented after they have seen that. Top row, middle row, or bottom row. And what he found is that participants for that row still could remember around 4 letters, no matter which row he indicated. So in a way, they were able to access each row, but then only able to report 4 letters in that row. So how can that be? The explanation for that lies in the very brief duration of these sensory memory stores. So in this register, sensory registers, information is extremely brief, and the information starts to fade away during recall. So while information is transferred into short-term memory so that we can actually recall it, all the other things we don't focus on fade from that store. So after we have named the 4th letter, the other letters are gone, just to decay. So we can name only 4 letters. However, by allocating our attention to a certain spatial area, we can decide which 4 letters we could remember. So before all the other information decays. So in the visual domain, this iconic memory is pretty much like an after image which fades away and which we can read out as long as it's still there. That's the basic idea of that. So the register itself has all letters available. However, it's not long enough available to name them all. And he, by using a little bit unusual way of calculating the memory span, but he said that the iconic memory, the span is around 8 to 9 letters. By different variations of matrix size and manipulations, he came to that conclusion. Okay, any questions on these sensory registers? By the way, the same or similar ideas hold for the auditory system, for the haptic things, so when we are experiencing touch and so forth. Okay, let's speak about verbal short-term memory. And this is actually defined in all models. In the Baddeley model, it's a separate short-term memory store. In the Atkinson model, it's part of the Unitary short-term store, which does verbal and spatial and visual information. And I think Cowan doesn't make any explicit statements on that. It's just the type of what type or nature the information has in long-term memory. Okay, again, let's do a demonstration. I will tell you a number, 4 or 5 digits, and I would like you to ask to remember or rehearse it until I say you can write it down. Let's say 3, 9, 5, 4, 6. Okay, please write it down. Okay, second demonstration. I will show you a number on the screen, and please try to memorize that number. And now write it down. Now the question is, now we use this absolutely invalid method of introspection. How did you do the task? So in the first demonstration, when I told you the numbers, when you did the rehearsal, how did you do it? Probably speaking it with your inner voice, didn't you? Okay. So verbally saying mentally again and again the numbers. How did you do it in the second task, when you saw the numbers? Probably the same, yeah. So very few, if at all, any person probably tried to remember the visual picture they saw here on the screen. They just went through that acoustically again, or verbally. So verbal information is encoded as a series of sounds, even when presented visually. So verbal short-term memory may contain, if you want to say so, visual information or information which has been presented visually to us. There are 2 very central pieces of information derived from studies which support this idea that our verbal short-term memory actually encodes the information phonologically and not in any other format. And one study comes by Conrad, and the first study he did was that participants were asked to remember and recall spoken letters with quite a bit of background noise. And what you will then find is that when people report them later on, that letters which are acoustically similar are sometimes confused due to the background noise. So it's hard to hear sometimes over a phone when you have to spell your name or whatever. For instance, M and N or B and P. You know, it's very hard to tell them apart sometimes. So it seems to be that there is this confusion. In the second study, he did basically the same thing, but this time the letters were visually presented. So really no point of confusing M and N or B and P. However, during recall, these type of confusions still occurred. So that led him to conclude that actually rehearsal is done in a phonological code. Because when we do it phonologically, we might confuse that in that format. And that is called acoustic confusion in our verbal short-term memory. A second study comes from, again, Alan Baddeley. And this now is what I mentioned briefly before. How many items can we hold in our verbal store? And if you remember, Miller suggested it's 7 chunks, plus minus 2. So based on visual information like letters, syllable, words, depending on how we can chunk that. However, Miller worked with this visual information, and we just heard that words are stored phonologically as sounds. And now the question arises whether that somehow affects actually our memory span. So let's have a demonstration again. Try to remember the following 5 words in order and write them down when told to do so, okay? Okay, probably most people have done quite okay. So these were the words you just have seen. Okay, let's do it once more with different words. Again, 5 words, shown for a time, then remember them and write them down later on, okay? Okay, these were the words of the second go. So, both times you had to remember 5 words. So, according to Miller, each word is an individual chunk, should be the same. Did you find them equally different, or was one more different? Probably the second one was more different. Why was it more different? I mean, some may say that words are harder to say, but you can show that's not the difference. The difference is that in the second example, you will have noticed the words are longer. It takes them longer to speak. And that is the so-called word length effect. The longer it takes you to say something, so to say the items, the less items you can remember. So when you have very long words, you may be able to remember only 2 words. If you have very short words, you may be able to remember 7 or 8 words. It's just the amount of time. So, and this is the idea which we had before. Verbal short-term memory seems to be time-limited, and it seems to be around 2 seconds. So everything you can squeeze into saying within 2 seconds, you can rehearse, you can store, and everything which is beyond 2 seconds, you can't. That's the basic idea of that. And it has been confirmed in many ways. For instance, when you have read the Gobet textbook, you will have come across that in Welsh, for instance, it takes longer to say numbers, just by the nature of the language. So Welsh people are not as good as English people in mental arithmetics and in short-term memory on numbers, because it just takes longer to rehearse them. Of course, they are not less smart as English people. So if you have Welsh people do the same test, or Welsh people who are bilingual in English, they show the same performance as the English people. It's just the limitation of short-term memory. So this also highlights, if you want to investigate something like IQ across cultures, you have to keep things like that in mind. And don't necessarily say, oh, these people are not that smart as other people, their IQ is lower. Has the IQ been culture fair, taking these things into account? Our short-term memory only cares for duration. If in our language it takes longer to say that, then we can rehearse less. Okay. Just maybe as a note, we now have seen that Miller actually proposed the amount of information is based on chunks, and now we have learned the amount of information is based on duration. Now, if you go more into detail, you can see that actually both factors contribute to our short-term memory, and either one or the other may be the limiting factor. And you can actually create mathematical models which integrate both views. So they're not totally contradictory, but it's going now a little bit beyond the scope of this course to unify both approaches. Okay, any questions on the verbal short-term memory? Yeah.
Can I just ask, I was wondering, yesterday in developmental psychology, we were learning about how babies, when they've read the passage from their mother's when in the womb, remember it afterwards, but obviously they can't rehearse it, and they just, how would they remember that being to do with sound?
Well, I'm not an expert on developmental psychology, I have to say, but this probably goes more along of the lines of priming. So when you heard something, then it's not necessarily totally lost. For instance, if it's information which can be relayed to information in your short-term memory, then there is a certain effect of recognition in that. And this is due to long-term memory storage then. So you can store things in your long-term memory just by a single instance. For instance, like names of people, you often have to hear them only once and you have stored them forever. So that can be an effect of that. And already small babies create memories in a way. So it may be such an effect of repetition and recognition. And to give you a proper answer, I would need to have to look at the exact age of the children and look that up. Okay? Okay, let's get to the last component here, to visual spatial memory. And here again we have the same situation as with the verbal memory. We have the visual spatial sketchpad, which is a separate component in the Baddeley model, while it's part of this unitary short-term store in the Atkinson model, and again not really specified in the Cowan model. And it was believed that short-term memory works in acoustic format, and it's very easy to investigate. So actually, when all the cognitive psychology arose, most studies just used verbal material. And it was only in the 1970s that there was a really seminal studies by Shepard and Metzler, which used this, you probably know that, mental rotation task. And that was a very early task to investigate spatial memory. And what they have done is the following. And they presented two three-dimensional shapes and asked the participants, are the shapes identical or mirror reversed? So let's have this example. In this case, who's in favor that it's the same shape? And who would say the two shapes are the mirror reversed copies of each other? Nobody. Okay, one person. It's the same. So if you rotate that back, you will see that this is this bit. What about this one? Same or different? Who is in favor of same? Who's in favor of different? Okay. It's the same. So this bit is this bit, so if you rotate it that way, then you will see that this is this bit. It's the same. Last one. Who thinks it's the same object? Who thinks it's mirror reversed? Participation is going down. Okay, it's the mirror reverse copy. So if you rotate it that way, that these two things, so like that, are in line, then you see this goes into the back, while this one goes into the front, so to say. So they did that task. That was a task to the participant, same or different. And what they manipulated was the angle, how much they rotated the objects. And what they found is that the time to decide whether it's the same or different linearly increased with the amount of rotation. So that the more you rotate, this is a degree of rotation, the more time it takes to make your decision. So that reflects that people actually seem to have a spatial representation of the object, and in this task what they actually do, they really, or we do that, we really rotate the object mentally. And we do it in an analog way, as if we would have the object in our hand and would move it at a certain speed. The more we have to move it, the more time we need to do that. This is not self-evident. It could be that we have just a three-dimensional representation of the object and we could directly match that. A computer would do it like that. It wouldn't slowly move around one object to fit the other one. So it seems to work in an analog way. Visual spatial memory. There are other examples of that. For instance, if you have to kind of move along tracks on an imaginary island, then you can show us the longer you have to move in your mind, the longer the distance, the longer it will take you to make certain decisions. Okay, any questions on visual spatial memory? Okay. Now this will only be a brief bit. Again, get to the control processes and the sensory executive system and the episodic buffer, a little bit of tidying up all the stuff we haven't spoken about in more detail. So the control processes are basically proposed in virtually all, I would say, working memory models. I would personally say short-term memory models, or short-term memory doesn't have or need these control processes. They are part of working memory. But that depends on the definition you will come across. And the exact function in each model varies slightly. However, there is some commonality in all models. So all say it has to do with control and coordination. For instance, what information actually is in short-term memory, by controlling attentional filters, by deciding which information is retrieved from long-term memory to put there. The flow of information between the different components, what I just mentioned. And the control of attention, I mentioned that, and the nature of processes we do, like mental arithmetics. That's in the domain of these control processes, so the manipulation of that. Then we have seen this episodic buffer, and as I said, that was introduced only pretty late or recently by Baddeley in the year 2000. And this really is one thing, because the original model had a little bit of a problem of how is information which is represented visual spatially and information which is represented phonologically, how is that linked? So when you see me speaking here in front, I create, hopefully, a unitary perception, a unitary percept in you. I'm one unit which has acoustics and a visual representation. So how is that linked? And the idea is that that happens in the episodic buffer. So when you see, for instance, a movie and you see an actor on the TV, then his words are represented in the phonological loop, his visual appearance in the visual spatial sketchpad. And at the same time, you may retrieve knowledge about this actor from your long-term memory. For instance, who is his partner at the moment, where other movies he has played in, and this can all be linked in together in the episodic buffer to get one unified representation. Okay, any questions on this last bit? Okay, then we are done for today. Next week we will continue roughly with that area and speak about long-term memory and learning about that. Okay, thanks for coming and see you next week.